Well, thank you for coming to my session. My name is James Weaver, and I'm with Pivotal, and we'll be talking about composing music in the cloud. And where we're going to today is I'm going to show you some things show you an application I wrote that does algorithmic composition, and I'll explain some things about music theory and specifically about counterpoint music. And then also we're going to dive a little bit into machine learning, and I'm going to discuss quickly machine learning, and then I'll show you a project that was created by the Google Brain team that does machine-based music composition. And so we'll jam with that a little bit. By the way, I have a session tomorrow with Catherine Beaumont, actually two sessions where we'll take deep dives into machine learning. The first one is an introduction. The second one will do some deep learning. So you're welcome to come to that, to both of those sessions. One is before lunch and one is after lunch. And then I'm going to give you a live demo of a piece of this algorithmic composition thing. So we'll be lots of demos today. So first of all, a little bit about me. I've been doing Java for a long time, written several books on Java and JavaFX, J2EE, as well as my latest book was Raspberry Pi and Java. So just kind of dive right into what counterpoint is. That's the kind of the subjective part of this. Counterpoint is the relationship between musical voices. So musical voices are like melodies, and they are interdependent harmonically. In other words, when two notes play at the same time, they must be pleasing to the ear. But they're independent in rhythm and contour. So the rhythms can be different, and the way that the pitches rise and fall can be different among the different melodies. And if you wanted to get a nice gentle introduction to that, then here's a nice link. By the way, these slides are on the web, and they're in my slides.com account, and I'm going to show you how to get to them very easily. So here's an example of counterpoint where we have 4 lines of music, and notice that we have different rhythms and different contours and shapes. And so I'm going to go ahead and play you then an example, and just listen for the okay. Okay, we'll start over again. Here we go. Again, noticing that the contours, the way that the pitches rise and fall are different, as well as the rhythms, but then every time 2 or more notes were played together, they sounded pleasing to the ear. So a little bit of history then. This person named Giovanni Palestrina in the 16th century created a version, or he kind of developed his own style of counterpoint called Palestrina counterpoint, and he had a lot of influence on musicians such as Johann Sebastian Bach. And then the next century, a guy with a very awkward last name, Johann Joseph Fuchs, who was born in Austria, by the way, he codified Palestrina's techniques. So he noticed in counterpoint, that particular type of counterpoint music, several rules. As a matter of fact, maybe 70 some rules for how notes should sound together and how they should follow each other. And so he documented those rules in this book called Gradus ad Parnassum. And so those described valid pitch and rhythmic relationships between the notes. So he influenced the music of Joseph Haydn, who is, I believe, was born in Austria, Mozart, and Beethoven. So, so there's in order to demonstrate this counterpoint composer application that I'm going to show you, that I developed using Java and Spring and some other technologies, I'm going to play this melody called, I guess it's Funkel, Funkel, kleiner Stern. Is that what it is here in Germany? Okay, very good. It's Twinkle, Twinkle, Little Star in the U.S. And so I think you've probably heard it before, but I'll go ahead and play it. Oops. That's Twinkle, Twinkle, Little Star. And I never get applause for that, so I brought my own applause track. No, don't. No, it's too late now. I'll just, there we go. I'll give myself my own applause here. By the way, if I don't get enough laughs, I'll just, I'll just pretend you're laughing here. So I better turn that off here. So that's going to be our main melody. We're going to use that for a main melody to our counterpoint, and then we're going to have this application that I developed then compose algorithmically other melodies that then are supposed to sound good with that and follow the rules of Palestrina counterpoint as documented by Johann Joseph Fuchs. So that's so there's an application called Counterpoint Composer, and I've got it right here. Let's see, Counterpoint Composer. All you have to do to get to it is type in counterpointcomposer.com, and if you go there, then this comes up in your browser, and then to get to the slides that I'm presenting, all you have to do is go to the help system. So the Getting Started guide, which is kind of what I'm going through now, is at this menu item, and then the technical presentation, all the technical things I'm going to show you are in this second one. So it's very easy to get to, counterpointcomposer.com. And so we're going to then start with Twinkle, Twinkle, Little Star. Now, in one of the slides, it shows you how to do this, but since I'm here, I'm going to go ahead and show you personally. So what we'll do, first of all, is we will click into the musical staff. That's where we'll be composing our music. And then I'm going to click the keyboard icon right here. And then I'm going to play a couple of notes just to get it started. I'm going to play two notes that will form the basis of, it'll tell us how many melodies we want in our counterpoint. I'm just going to specify two melodies, and then I'm going to play the rest of Twinkle, Twinkle, Little Star. So, so here's the first two notes that will play simultaneously. And then you see that they're being entered there. So, okay, so we've typed in our cantus firmus, and now we want to compose. So there are a couple of options here. We can choose the species. So when Fuchs, when he codified these rules, he noticed there were about 5 different species of counterpoint, from easiest to hardest. And so when he wrote the book, Gradus ad Parnassum, gradus means stairs in Italian. And so it was this idea of taking a student through the different species, first through fifth, and so the rules kind of progress. So the easiest one is the first species. And then in music, there are 7 different modes that are, if you play the piano or have seen a piano, then you have white keys. And so the Ionian mode, for example, is kind of centered on the C key, and usually begins and ends on C and has a very bright feel. There are other modes like Dorian or Aeolian mode that have kind of a darker feel, and so you'll see that in a minute. But I want to go ahead and start out with Ionian mode and in first species, and now I will say, now that I've punched in my cantus firmus, I will compose. And so now it is going to the cloud, using microservices in the cloud that I'll show you, to then compose the counter melody here. So this is the one I punched in. I also punched in this note, as you'll remember. So I wanted 2 lines in my composition, in my counterpoint, and then the microservices then composed according to the rules that were documented by Fuchs. It composed this second one. So let's see how it sounds. Let me go ahead and play this. I'm going to make it play a little faster than the default, maybe 200 and some beats per second or per minute. That would be fast if I did it per second. Okay, so there's play. Okay, so you'll notice that even though it was rhythmically different, the pitch contours were different, the notes sounded good when they were played together. I want you to notice a couple of other things as well. Notice the D5. Everybody see the D5 and the A5 up there? Those are chord signatures, chord markings, and those will come into play. But basically, anytime 2 or more notes are played together, then the counterpoint composer, the microservice in the cloud, then tries to identify, is that a chord? Is that a known chord? And if it is, then it returns and tells it, and then we put it on our score. So that's how we enter a cantus firmus and we compose. And so here are the steps to the demo, and you'll be able to run through that yourself. And so those are just the things that I said. And here are some resources if you'd like to learn more about counterpoint or first species counterpoint. And then also some tips on composing a cantus firmus, a main melody. So now we'll go to the second species. The first species, as you'll notice, was a whole note and on top of a whole note. So there were the same values as far as time. Note on note counterpoint is what it's called. The second species contains half notes in the counter melody. So there's 2 half notes for every whole note. So I'll go ahead and go back to counterpoint composer, and I'm going to specify second species. And we'll go ahead and hit compose. And then we'll play that, again speeding it up a bit. Okay, I'll just type in 240. That'll be easier. Okay. So that's second species. And then if I wanted to go to third species is quarter notes. So for every note in a cantus firmus, there are 4 notes going on in the counter melodies. So I'll go ahead and say third species, compose. and then we'll play that, and we'll see what third species sounds like. Okay, and then fourth species is called florid fourth species will have two half notes, but it's kind of has a nice feel to it, and I'll explain why. Let me get up to fourth species here. Okay, so if you look at the notes there, you'll notice there's a tie. That's this kind of half circle or arc between two notes. And so you'll notice that the half notes are the same between measures, so they kind of cross the measure. And so what that does is that builds this idea of a suspension and kind of a release. So you'll notice as you're listening to this one that at the end of the measure, the last beat of the last note of each measure, it'll play this interval that has this feeling that it needs to be resolved, and so there's this suspense there. And then when it gets to the next measure, then you hear the resolution. And so I'll go ahead and compose with the fourth species, and then we'll play it. I'll play it a little bit slower so that you have time to hear what I was talking about as far as the suspend and the resolution. So listen for it. Suspension, resolution, suspension, resolution. So I misled you. I misspoke, actually. The suspension is actually on the first half note of each measure, and the resolution is on the second half note. So I'd like to you to listen to it again in that light. You hear that? Suspension and resolution? So that's part of the fourth species of counterpoint. Okay, then the fifth species is called florid, and it combines all of the other species, plus it adds eighth notes. And you have various rhythms, things. So it's very creative in terms of counterpoint. So that's this one. That's fifth species. And so you'll notice in the counter melody, lots of different variation. So we'll go ahead and click fifth species here. And compose. It couldn't compose. There we go. And then we will speed that up to maybe 200 and play. Sounding more like a classical piece. Okay, and again, there are links if you want to learn more about fifth species. So that now there's something called modes in music, and I talked about them a little bit. There are 7 major modes from Ionian to anybody musician here. Anybody can tell me what the last mode is? Yes. What's the last mode?
Oh, I don't know.
Okay. I'll give you a hint here. Here we go. Locrian mode. So, and Locrian is all the white keys again from B to B, and so Dorian is from D to D, etc. So. So what I'd like to do then is kind of explore the modes in music. So what we can do then is compose something that starts in D and ends in D, and we'll select Dorian mode from the counterpoint composer, and we'll hear something that's in that vein. So I'll go ahead and clear here. Didn't mean to put you on the spot. Okay, so again I say Dorian mode, first species, and we'll just go ahead and compose something that starts with D. Whoops, you have to click in there. See? Now I want you to just kind of notice that this has a little bit of a darker feel, kind of a minor feel. So I'll go ahead and compose. And then we will speed it up a little bit and hit play. Everybody hear that it just has this darker feel to it. And so there's a video on doing that. So you can also, using Counterpoint Composer, this is actually being used in some universities, and the students are able to experiment with turning off and turning on these rules. So again, there are 70-some rules, and they're listed in this application. If I go to the Rules menu, they're listed in order of importance. So here are some rules with critical importance. Like there's something called parallel fifths that were very common with Gregorian monk chants and things like that. So they sound good in those chants, but they don't sound good in counterpoint music. And so parallel fifths are not allowed in counterpoint music, for example. So here are some critical ones. Here are some ones that are with high importance, and then here are some with medium importance. And I'm going to pick on this one, this rule that says avoid unisons in two-part counterpoint. So I'm going to go ahead and disable that rule so that it should allow now unisons in two-part counterpoint. So here we have two parts in our counterpoint. And I'm going to go ahead and, now that I've turned that rule off, I'm going to go ahead and hit Compose again. And I'm going to go ahead and play that. And I'm going to point out that it did, in fact, allow a unison. And I'll explain what a unison is in a second here. But I want you to hear it first. So we'll play that. So that last note, you only heard one note. I'm going to go ahead and play it again and listen for the last note. So that's called a unison. When you play more than one note and it only sounds like one note, that's unison. And so if you look at the last measure, in the treble clef, which is the upper clef, the one on the top, we have a D. In the bass clef, even though it looks different because it's in a different clef, that is also a D. It's the D above middle C. So they're both the same one. So when we switched off that rule, it allowed it to put a unison in two-part counterpoint. Another thing that you may have noticed is that the counter melody that was generated was different. So if you disable a rule or change a rule, then it affects, because of the algorithms, it affects the entire melody, or it could have a potential effect on the entire melody, because there are things that are dependent upon different combinations that are happening in the composed counterpoint. So the fact that it allowed a unison allowed other things then to happen. It caused the melody to change. So that was the effect of disabling it. And so now I'd like to then kind of dive into the technical portions of this. So we did some composing music algorithmically. I demoed Counterpoint Composer. So now I'd like to show you the high-level architecture for this application. So first of all, we have a single-page HTML5 application. And so we have some common functionality drop-downs, things like that. But then also we have a plugin called NoteFlight. Now, NoteFlight is if you can just go to noteflight.com. It's a site where you can compose music, but they also have a plugin that you can embed in HTML applications. And so in this case, what I'm doing is that I'm embedding it so that I have the use of the staff and the keyboard and the ability then to allow the user to compose something. And then when they compose a cantus firmus, then what we do is we send that information up about the melody and some other things to a microservice that's running in Pivotal Cloud Foundry. And the microservices are created in Java, and they use Spring and Spring Boot. So there's one called Counterpoint Service. So we send up some information about the melody to Counterpoint Service, and then it calls Chord Analyzer Service. Now remember, Chord Analyzer, we analyzed the chord and we showed what kind of chord it was, and we put that on the music. So that's the job of the Chord Analyzer Service. So we have these two separately running independent microservices that then are combining to provide this functionality. So that's the architecture. By the way, if you have any questions while we're going along, please do ask. I'll be glad to answer anything I can here. The source code, this is completely open source. It's Apache 2 licensed, so it's in GitHub. Here's the Counterpoint service in GitHub. And to kind of dive into then these microservices and what their functionality is, if you look at the top, there's the cantus firmus that we created. So there's the three chords, or the three notes. We used 2 notes when I demonstrated it, but you could use 3 or more if you'd like. And then there's the melody. And so we create a JSON string out of that in the HTML5 application, and we send that to the service. So the JSON string consists of the main melody, which is a numeric representation of the melody in something called MIDI, M-I-D-I, which is a standard for representing notes. And then we send the parts in the initial note, which indicates how many parts we want. And then we also send the mode and the species of counterpoint that we want. So then that's a post to the Counterpoint service. It then returns some XML that is in this dialect called music XML, which then expresses the whole composition that was created when the service created counter melodies and used all the rules that that Fuchs documented. And so it sends back the melody in music XML, but then when more than one note is being played at the same time, we want to be able to note that on the score, and so we call that Chord Analyzer service, passing in notes. In this case, it's a G chord, a G3, D4, B4, and then it sends back information about the chord, like the root of the chord is G, the chord type is major, the bass note is G, and then we can, in the HTML5 application, then we can put that on the score. So that's kind of the cycle of what happens with these REST services. Created in Java, and it has a kind of a legacy of Fuchs created and wrote a book on those rules, and then other people before me have ported those rules to languages like C. My contribution was I ported it to Java, and then put those in microservices there and put them out in the cloud in Pivotal Cloud Foundry, so then anybody can use them, and including universities and things when they want to learn about how to use Counterpoint. That's kind of that in a nutshell. And so I'd like to explore a different approach now to music composition, if you don't have any more questions about this particular approach. So any questions? Okay, so I'd like to switch gears a little bit, and we're going to come back to Counterpoint Composer. But there are other music composition approaches that have been taken over the years. For example, back in the 1800s, it used to be a fun parlor game to have music notation, bits of music written on the face of dice. And then people would roll them, and then whatever came out, then they would play. So that was a way of kind of randomly generating music. More recently, then, Google Brain has created this open source project called Project Magenta. And this is this idea where we have this artificial intelligent agent that uses machine learning to receives notes, kind of to seed this artificial intelligent thing, and then it responds using machine learning to what was played. And so you can kind of go back and forth, kind of jam with this neural network. So that's Project Magenta. And so I want to set the stage a little bit on what machine learning is. And by the way, Catherine Beaumont and myself tomorrow will be giving some deep dives in machine learning. But in a nutshell, machine learning it's right there, is the science of getting computers to learn without being explicitly programmed. So if you recall with Counterpoint Composer, I had to algorithmically create an application that in Java that would express all 70 of those rules and then create those counter melodies. With machine learning, you don't explicitly have it learn something. You don't explicitly teach something. The machine learning mechanisms like neural networks, they learn how to do something. And so the teaching that you give it would be with data. So either supervised or unsupervised. So here's an anatomy of an artificial neural network. It's basically modeled after the brain. Over on the left you have inputs, and on the right you have outputs, and you have hidden layers in the middle that are analogous to your neurons and synapses in your brain. And so very simply, kind of a very simplified view is over on the left you have an input. Let's say you have a picture. Well, a picture is made up of pixels. So your input might be, a 24 by 24 picture so it has whatever 24 by 24 is pixels. And then each of those pixels would actually have RGB values. So you might have 3 times that many inputs, each having a 0 to 255 value. And so that's your input. And then you have layers in your artificial neural network that then take process that input and try to it can then learn by you training that input with some output. For example, the initial picture on the left, you might want to train it on recognizing a cat and an elephant. So there's an elephant, and so we would give it many pictures of elephants, and we would tell it that's an elephant. And then in this is a very simplified view, but in the hidden layers, then it begins to put values in the neurons as well as in the synapses, those edges in the graph, put values that then trains it, that then represents weights that then cause it to, when it recognizes an elephant, to know it's an elephant, or when it sees an elephant to know it's an elephant. And so in the middle there, it's in the hidden layers, it's beginning to build up representations of things that might be in an elephant, like tusks or eyes, or if it's a cat, like fur and eyes. And so that's how that works. And so that's supervised learning in a traditional neural network. There's also something called a recurrent neural network, and that if we're recognizing a cat or an elephant, then that's something where it's very static. You're giving it a picture and it's saying what it is. You're asking it to classify what it is. But if you have time series data, like music is time series data, so we have a melody and one note comes after another. Excuse me. So one note comes after another. You need to be able to capture the order in which these notes happened, to be able to then predict the next note or compose the next note. So to illustrate this, let's say that it's you have a couple of cats in a box. So if you were giving this to a supervised learning technique, a normal artificial network, it would only be able to tell you that there's two cats and a box, but it can't tell you what's going to happen next because there's no time series data with it. But then, I had a lot of fun on Giphy, by the way, finding this, but it turns out that what's going to happen next is the cat on the top is closing the box. But it could have very well been that the next thing that was going to happen is the cat on the bottom would open the box. So how does that relate? Well, we have this thing called a recurrent neural network that can then make a prediction. So if we give it a certain number of notes, let's say I'm playing some notes, and we're asking then the computer, the neural network then to jam with me. We're asking it to then play some notes that might happen next. So with this recurrent neural network, we can play some notes, and then it can then predict based upon probabilities that it's observed in a body of music and in this particular case, they've trained Project Magenta with everything from Bach to Radiohead to different other groups, just a wide variety of music, of melodies in the music. And so then it can make these predictions with its artificial neural network. So it extracts melodies from songs, and then if you look at this diagram, this is depicting a recurrent neural network. So we have at the start, we have, you can see below start, there's no notes. So we don't have any notes. And so the recurrent neural network might say, okay, if there's no notes, I'm going to play a C, because the body of work that I analyzed, the probability, if there's no notes, for the next note to be a C is highest, and so it would play that one. And then we feed, in this particular case, we feed that C back into the bottom, and now we have C and C. And so then the recurrent neural network says, the next note, the highest probability of the next note when two C's are played, then would be a G, and so on. And so that's a simplified version of what's happening. The same type of thing also happens for rhythm. So half rests and quarter rests, or the durations of notes or the absence of notes. Those things are studied as well, learned by the recurrent neural network, so then it can make predictions on what note should be next. So they created a demo called AI Duet and the link, by the way, is here, so you can play with it anytime you want to as well. And I'll go ahead and hit play. And I'm going to play this, actually, I didn't show you this before. This is a MIDI keyboard. It's called a Linstrument. It's got 250 keys, 8 by 25, actually 200 keys. And it's a very expressive instrument. Plays a little bit like a keyboard, piano, but also like a guitar. It's laid out a little bit like a guitar, so it's a really nice, fun instrument to play. So I'll just jam with it a little bit. So first of all, I'll play just a typical 1-4-5 chord pattern. That's a pattern that you'll recognize in lots of different songs. And so it's now playing back based upon these probabilities that it's learned in the recurrent networks. Who's heard of Close Encounters of the Third Kind? I thought it'd be. Remember the movie Close Encounters of the Third Kind? Anybody has heard that? Okay, there was it's about a spaceship, an alien spaceship, and so they're trying to communicate with it, and so they found that they figured the best way to communicate with it would be to play a melody, and then maybe it would play a melody. And so I thought, well, it'd be kind of fun, kind of appropriate. So here was the melody that they played. It was just four simple notes. The fact that this is here is messing things up a little bit. Okay. Okay, so then we could also kind of jam with it, play a song, Frere Jacques. So it kind of plays, kind of jams with you as you're playing. And it does it with a neural network. So now I'd like to go back to Counterpoint Composer, and you remember that second microservice that identifies chords and then puts them in the music. That microservice is, as is the whole thing of Counterpoint Composer, is written in Java, and it uses Spring and Spring Boot. And so it's really easy to create a REST service with Java and Spring. You just create a REST controller, and then you give it a class. And so this is now my REST controller class, and then I can give it endpoints like analyze, and then I can associate that endpoint with a method like analyze. If I say /analyze in my REST service, then I can it'll call the identify chord by notes. And you remember we passed some notes to it, so those would be passed into this, and it's very easy then to stand up a REST service. If I want to, because the notes and the chords are serialized over the wire between the client and the REST service, I need to represent those. And with Spring, you can easily represent those with plain old Java objects, POJOs. And so this represents a musical chord where we have the root and the chord type and the bass note. And so you just do that, and then it automatically marshals it, serializes, deserializes over the wire with JSON or XML, whichever one you choose. And then to make the app executable, then you use the Spring Boot application annotation, and then you have your application, and then you just say Spring application run, and then you give it the name of your Spring Boot application, and then to deploy it in Cloud Foundry, it's just 2 steps. My whole development cycle is 2 steps. You just do a Maven clean install, and then a CF push, and CF push pushes it into Cloud Foundry. Cloud Foundry, by the way, can run on top of AWS, Azure, now Google Cloud Platform. So you're just putting it in, pushing it to one cloud platform, and not having to worry about the underlying IaaS. So I'll end with this, demonstrating the Chord Analyzer client. So that was a separate microservice. Remember over there on the right. And so as I play, I'm going to play on this instrument. And as I play, the notes that you see are going to be locally from this instrument. The chords that you see are going to be after those notes have been sent to that second microservice and then back and identified. And I'm running it through my phone hotspot, so should be pretty good response time. And even though it's running through a personal hotspot and it is running in a cloud in the eastern side of the United States right now, we should still see a pretty good response time. So to demonstrate that, I'm going to play some Bach Prelude in C and see if I can do it without butchering it too bad here. Doesn't sound good. Oh yeah, that's okay. I need to turn that off. There we go. That would help. Hmm. 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 So anyway, as I play chords, notice that as I'm playing them, then it's showing then the actual chords that are represented. So anyway, that's my presentation, but that's in a nutshell composing music in the cloud. Thank you.